One important aspect of operating system design is efficiently and correctly handling processing in systems where we have access to multiple processors. So in this video, we're going to lay the groundwork for understanding systems with multiple processors, which we call multiprocessor systems, and we'll build on this in the lectures. What I need you to recall for this video is the topics from discussion from last week, where we were talking about scheduling on systems where we looked at it purely from the perspective of a system which only has a single processing element, so a uniprocessor system. So first, it's useful to have a definition of different kinds of multiprocessing systems, and we are going to present them here in three broad categories. The first category is what we call functionally specialized multiprocessors. So this is where we may have a general purpose central processor, and then we have several slave processors, each of which has a specific function. So that's what we mean by functionally specialized. So here we have an example of a DVD processing system. So it's what we call a heterogeneous multiprocessing chip. And in this case, it has 6 cores, where one core is the main control processor, and each of the other cores has a specific function that they work on. So one is an MPEG video decoder, one decodes the audio, one handles composite video encoding, one controls the disk, and one is a cache processor. The second broad category is what we call loosely coupled multiprocessors. So in this case, we have a system which has multiple processing elements, so multiple CPUs, but the degree to which they are coupled by their memory requirements is what we call loose. And here I've stolen from the Oracle documents 2 examples of what we can call loosely coupled systems. So on the left, we have a multiprocessor system with 5 nodes, each of which might have multiple processing units, but they have their own individual shared memory, and here in this case they are coupled by a shared disk. Whereas on the right we have a even more loosely coupled system here, where each compute element has its own individual memory and disk elements. So there's almost no coupling, and any communication that does happen happens between the CPUs like this. So for example, we have an example data path where if CPU 2 needs to somehow communicate with the data that the first CPU is happening, it has to go through the first CPU in order to access that memory. Now the final type of final general type of multiprocessor that we talk about is called tightly coupled. So in this case, we have multiple processing elements, but they share one overall pool of memory, and they share disk. Now, as you progress through this course, you'll realize that we can often treat them as one and the same, but the key factor here is that communication in this case can happen through the shared memory, and the tightly coupled kinds of multiprocessor is what we will focus most of our discussion on. So as I said, we're primarily concerned with tightly coupled multiprocessing, so the kind that I presented on the last slide. Some of the benefits that we can have through this particular regime are reliability through redundancy. So in this case, if a single node goes down, a single computing element fails, we don't have complete failure of the system, we just have a loss of efficiency, since the slack can be picked up by the other computing elements and the system can continue. So that's one advantage of having a multiprocessor system in this regime. There's also programming convenience. Because the memory is, the overall pool of memory is shared, the level of difference as far as the programmer is concerned from a uniprocessor system is much lower than with loosely coupled or functionally specific multiprocessing systems. So it can be more programmatically convenient to handle tightly coupled processing. Indeed, in many cases, the programmer can be completely agnostic to the fact that there's multiple processing elements available. And finally, the most obvious benefit to having a multiprocessor system is the performance benefit, since we can either design algorithms that can handle the multiple processing elements with shared memory carefully, or we can offer multi-programming support. Okay, so we've categorized multi-processor systems, i.e. the hardware viewpoint, and now we will briefly categorize parallelism, i.e. the software viewpoint. And one of the ways in which we can categorize it is in the level of granularity. So how often do independent threads of execution synchronize with each other? So the first level of synchronization granularity is actually the least amount of synchronization, and that is absolutely none. So we call this independent parallelism. Different jobs are run independently on different processes in our multiprocessing system, and there's absolutely no explicit synchronization amongst the processes. A typical use of this might be a time-sharing system, and it's not incredibly different from having just a network of multiple workstations, but it might be a more cost-effective approach. So the next level up would be, we would categorize as coarse or very coarse-grained parallelism. So processes which synchronize at a very gross level. We can easily handle this on a system which only has a single processor using a set of concurrent processes, like we discussed last week. So in this case, we can support this on a multiprocessor with very little or no change to the user software. An example of a coarse or very coarse-grained parallelism would be a process which spawns several children, each of which run on separate processes, and the results are then accumulated in the parent process. In this case, we have a very wide time gap in terms of the number of instructions between synchronization of the processes. So what we've got there is an example of a range which we might consider to be in the coarse or very coarse grained range. The next level up is what we are calling medium-grained parallelism. So in this case, we might have a simple application that can be implemented as a number of threads. So at this level, the parallelism can be maybe being specified by the programmer itself. There needs to be a higher degree of coordination and interaction amongst the threads of the application, and this leads to the medium-grained level of synchronization. In this case, threads may interact quite frequently, and scheduling one thread may affect the performance of the entire application. So if the threads are incorrectly scheduled, then how quickly the overall process finishes ends up being affected to a higher degree. And again, we have a tighter window in which synchronization tends to happen. And at the very furthest end from independent processes, parallelism, is fine-grained parallelism. So this is an even more complex use of parallelism than we would see in the use of threads, for instance. So in this case, this requires that the programmer may use special instructions or write inherently parallel programs. There tends to be these tend to be very specialized. So each individual problem that has to be handled has to be done in a very different and specialized manner. And the implementations tend to be fragmented with many different approaches. At this point, we are considering parallelism where we have synchronization within a handful of instructions, and maybe even at the single instruction level. So now we have a categorization of multiprocessor systems, and we also have a categorization of different levels of parallelism. And when we are designing a multiprocessor system, we run into a number of design issues. And the scheduling method that we use, or the scheduling decisions that we make in a multiprocessor, involve three different issues that are all interrelated. So the first is how we decide to assign processes to processors. So which process goes to which CPU, and how and when we decide to potentially change that. The second is how we use multi-programming on each of the individual processors. So we discussed last week on scheduling on a uniprocessor. A lot of those same issues still exist even when we have multiple processors for each individual CPU. And finally, we have issues related to the actual dispatching of the process. Now, the only thing that we are going to discuss in this video is the first, and we're going to give a brief introduction. The last two will be discussed in lectures. So the first way we can break down the assignment of processes to CPUs is whether the assignment is static or dynamic in terms of the lifetime of the process. So in the static regime, when we assign a process to a CPU, it remains running on that CPU for its total life of the process. So each CPU will maintain a short-term queue and choose from that queue which process to run next. It's a very simple approach, and there's less scheduling overhead, because once we assign that process to the particular CPU's short-term queue, there's no more reassignment between the processors. The main disadvantage, however, is that one processor might remain idle while the other one has a very long queue. So if we have a bunch of short processors to run and a bunch of long processors to run, and all of the short ones are scheduled for one CPU and all of the long ones are scheduled for a different CPU, we can see how that's far less efficient than if they were evenly distributed between the two CPUs. The second regime is dynamic. So in this case, a process can move, in the dynamic regime, a process can change between different CPUs during its lifetime. So it may be scheduled, say, to CPU number 1 at the start, but at some point of interruption, it is rescheduled to a different CPU for the remainder of its execution. In this case, we would maintain a single global queue for all of the processes, and then we schedule individual jobs for whichever processor happens to one of the available processors. This is obviously more efficient, particularly, for example, in the case that we were discussed as a disadvantage of the static situation, but it can be more complex to manage and involve more overhead. Another aspect in which we can discuss the assignment of processes to CPUs is in terms of the means in which we assign them. So we can think of two particular architectures, a master-slave and a peer architecture. So in the master-slave architecture, one particular CPU is important. The operating system runs on that particular processor and schedules its tasks off to the other processors. The control of resources is fairly simple, and we don't require a lot of changes from the uniprocessor multi-programmed operating system style that we've discussed in the previous week. The problem is, though, that the master CPU can become a bottleneck, and we lose some of the reliability benefits that we talked about earlier in the video, because if the master fails, the whole system fails. The second architecture we've discussed here, the peer architecture, it involves having the operating system run on any particular processor, and effectively the processor schedules them itself. It makes the design of the operating system more complicated, and we do have issues of conflict resolution, such as two processors trying to compete for the same job or the same resource, and handling that conflict resolution adds complexity to the system, but we do regain the redundancy benefits that we lose in the master-slave architecture, and we prevent the control being a bottleneck. So in this video, we've discussed multiprocessor systems as far as an operating system is concerned. So we've covered the types of multiprocessor system that we might have, and we narrowed down to the tightly coupled multiprocessor system, which is what we will focus most of our attention on. We also talked about the different levels of parallelism that an application might have, and this was with regards to the synchronization granularity. And we discussed and introduced some of the design issues that occur when we start handling systems which have multiple processing elements. And we gave a brief introduction of one of these design issues, which was the assignment of processors to CPUs.